The assembly shown in the figure is welded to collar A that fits on a vertical pin. The pin can exert couples about the X and Z axes, but does not prevent motion along or about the Y axis. So, there's a lot of keywords in there in this problem. The pin can exert couples about the X and Z axis, but does not prevent motion along or about the Y axis. So, drawing our free body diagram is a good way to start off every time. We know that we have an A of Z reaction force, and we also have the moment about AZ. So moment AZ. We also have AX, and we also have moment AX. We also have tension pointing from D to E right there. We also have that weight going down, and we also have TC to F. Oh, TC to F. That is all the forces in our free body diagram. So we need to find the tension in cable CF, the tension cable DE, and the reaction and the moment at A. The way that we can do that is by first, remember we know the equation TCF is equal to the unit vector CF times its magnitude CF. And if you solve for the unit vector CF, we know that it's equal to position vector from C to F over its magnitude. That will give us negative 0.08 I plus 0.06 J, and then we take the square root of the square root of those components. So 0.08 squared plus 0.06 squared, and that's the unit vector. We can do the same thing for the tension from D to E, which equals U dE T dE times its magnitude, and we'll get that U dE is equal to 0.12 I minus 0.09 K. And then we do the same thing. We take 0.12 squared plus 0.09 squared. And that's our UDE. So now from the free body diagram, we can take our f of y equation, set that equal to 0, and we'll get 0.6 TCF plus 0.8 TDE minus W is equal to 0. And we can also take the moment about the y-axis, set it equal to 0, and we'll get that negative 0.8 TCF times 0.135 meters plus 0.6 TDE, 0.08 meters, and set that equal to 0. And now we have an equation with two equations, two unknowns, TCE, TDE, TCF, TDE. And we already know the weight, which I was given is 560 newtons. So we can solve that system of equations, and we'll get that TCF is equal to 233 newtons, and TDE is equal to 525 newtons. Now, we can also solve for a of z and a of x by taking f of x equal to 0 and f of z equal to 0. For our f of x equation, we'll get ax minus 0.8 tcf equal to 0, and we'll get az minus 0.6 tde is equal to 0. And we know the tensions now, so we can just go ahead and solve for ax and az. Ax is equal to 187 newtons, and az is equal to 315 newtons. And then to find the moment about az, you can just set moment az equal to 0, and you can write a as a vector, which is equal to 187i plus 315k, and then you have enough information to find the moments ax and az, and that is that problem.